All right. Good afternoon, everybody. Today's April 4th, 2023. Welcome to SEVA VentRounds. And today we're going to discuss a case that we had that I believe it's a must recognize. And it's not a common thing that you will see, but once you see it, your eyes will be open to the beauty of it. And so the aim here, and obviously the title, Discordant Resistances, is probably starting to get you into the feeling of what this is all about. So let's get started. The first thing is our disclosures. We will discuss particulars of ventilator modes. There's no endorsement of any particular mode or manufacturer or company. And whatever we say, it's our opinion. It does not represent the Cleveland Clinic. My disclosures are there for fees and royalties for books and chapters and consultancy, but nothing essentially related specifically to what we're going to be discussing today or the case today. Rob is out in vacation today, so you got me. All right. The ground rules is this is a recorded session, so keep your microphone muted. The chat is very efficient. Any questions as they're coming out, even if you feel that this is something that is so obvious that nobody would ask it, because actually it brings a lot of knowledge to all of us when we see these things. And then if you want to comment or you want to say something, you can put it on the WebEx, on the chat, and I will happily ask you the question, and you can unmute yourself and be part of the conversation. So no fear. This is a safe space where we're all learning. For those that are respiratory therapists, remember that we offer CRCEs, and so just enter your name in the chat to verify that you're aware attendance, and at the end of the chat, in half an hour, you'll see the QR code where you can get your evaluation you completed, and then you get high quality points for it. All right, so as every bent rounds that we do, we start with some key knowledge, and what I want you to focus today is on the knowledge of how to recognize the resistive load, meaning an increased resistance. Remember that the pressure waveform when you're in volume control manifests both the resistive and the elastic load. In this case, we're going to focus on the resistive load. And so during inspiration in volume control, you will see the changes in the pressure waveform. And during expiration, because what we're controlling during expiration is the pressure, because we control PEEP, then we look at flow. So during inspiration, you look at the pressure waveform when you're in volume control, and during expiration, for all modes, you always look at the flow waveform. And so here I have put a square flow waveform and a ramp flow, or a descending ramp flow waveform. And there's, without a doubt, there's ventilators that can alter how these waveforms look. Some can delay how fast it takes to peak and where the end expiratory flow ends. But this is the idealized form, and this will help you to kind of put into context what is happening. Now, when you're looking at the resistive load, you have to recognize that the resistive load is, according to the equation of motion, is resistance times flow. And so if you set the flow higher, then you will have more of an elastic load, resistive load, or if the resistance is high, you will have more from that. So what you see here is an increased resistive load. So you see a high step up at the beginning, because the first thing that the flow encounters, you're controlling the flow, the first thing that it encounters is the resistive of the endotracheal tube, the trachea, the bronchi. So you see that increased rapid rise. And then the rest of the slope is actually the elastic load, is determined by the elastic load. So right now we're talking about resistive. So the first step up is always resistive. And then if you stop the flow at the end of the breath, I mean, over here, the end peak inspiratory pressure is a manifestation of both the elastic and the resistive load. If you do a pause, an end inspiratory pause, you will see only the peak as it goes down, all the resistive load, because there's no more flow, you will only see the elastic load. So this is another way to recognize that the resistive load is high. But just by looking, you could rapidly, if it's a square waveform, you would recognize it by this, by the presence of a high step up. Now, during expiration, you will see that, well, we're going to go in expiration in a second. If we go to volume control with a ramp flow, the maximum flow is at the beginning of the breath. So you set the maximum flow is going to happen at the beginning, which means if we recognize the resistive load as a manifestation of flow times resistance, at the beginning the resistive load is going to be the maximum, and you can see here as the system pressurizes, with the resistance and the high flow, you see a rapid step up, just like as you saw over here. You see a rapid step up, this rapid step up, and over here this step up. That's all resistive load. And then as the flow decreases at the end of the breath, actually you don't see, there's no flow, so there's essentially no resistive load. No resistive load. It's all elastic. And so when you see this, when you're recognizing an increased resistive load and it's a descending ramp, then you would expect to see a high peak at the beginning on the pressure, and then it will go down to demonstrate the elastic load. So the key items here to recognize is a rapid step up in both, but if it's an increased resistive load and you're on a descending ramp, volume control, you should see a high peak and then it will descend to the elastic load. So this waveform that you see here is characteristic of high resistance during inspiration. Now, normally, in most cases, you're going to have concordant resistance. So you will see high resistance during inspiration and during expiration. And so as you see on these two cases, you see that the time to reach zero flow is prolonged on these two cases. It's taking a long time to reach zero flow. There's still flow at the end of the breath, which tells us that the resistance or the time constant is prolonged, and so the resistance has to be prolonged. The same that happens here. So you see that it takes a long period. So normally you see both happen. So if you see high resistance here and you see high resistance down here, that means that the patient has high resistance. Now, there could be situations in which they are discordant. All right. Now that I have said that, here comes the waveform. So I want you to observe very carefully this waveform, and I'm gonna just for the sake of it, put what the tag is, which is volume control, CMB, S. So meaning we're controlling the volume, so it's a descending waveform, all right? It's CMB, meaning that all breaths it's a continuous mandatory ventilation, so all breaths are mandatory, meaning that they are triggered either by the ventilator or the patient and cycled by the machine. In this case, all the breaths are cycled by the machine, so that makes them mandatory because we're controlling the timing and the size of the breath. And finally, set point, because we set the tidal volume, the inspiratory time that the patient is going to get. So we're setting the variables for it. There's no intelligence built into this mode. So I'm going to ask you, as you go through this, and you can put it on the chat, what is the load during inspiration and what is the load during expiration? So you have two breaths here, but you're happy to type at will. So what's the resistance or elastance or PMOS? So if you see any evidence of PMOS during inspiration and expiration, what is the PV discordance? So the patient ventilator discordance in terms of trigger, inspiration, cycle, and expiration. So I'll give you a minute to observe, or 2 minutes actually. This waveform needs to take a look at it, think about it, and please write what you think is the load during inspiration and expiration. And I'll ask, evidently, our team to start thinking about this. This is a key waveform, and actually this is from a true patient. I was walking, but actually I was running on the patient, and this is the first waveform that appeared in front of my eyes. So have no fear. This is not a simple one. So if you're feeling sad and saying, "Geez, I should know this," don't feel like this. This takes some time sometimes to recognize. So have no fear. Thank you, Sarah and Sherry, for sharing. Keep putting them in. I'll give you 1 minute and we'll go through it. So what is the good? Starting to get some answers. Good job. Mm, I like it. All right. There's a lot of interactions here. Good. So obviously the people let's walk. I'm gonna walk you through this so we can go through it. So let's start with the load. And the load, when we watch the first breath, the first question is always if there is PMOS to me, and because we're controlling the flow during inspiration, I have to look at the pressure waveform. And as I look at the pressure waveform in this circumstance, I know it's a descending ramp. And so I'm going to show you, I'm just going to go back for a second, and I'm going to show you the ideal, how it looks. And you see here the initial ramp up, then this curvature that occurs, and then it ends over here. And I want you to see it down here, how close it is. There definitely there's a little bit of increased resistance, but it comes down, and the difference between peak and between the peak pressure up here and the end inspiratory pressure is very small. And actually you barely see, you don't see a major deflection that would say there's a lot of PMOS. So I would say that if I looked at this waveform, I would say my initial thought that this is probably normal and the main load is elastic with some degree of resistance. Without a doubt, there's this little bump over here. So, but it's not a major bump. And actually, if you see the next breath, which as many of you have recognized, this is what we call a double trigger, and because it's on volume control, the patient got another breath of 440 milliliters. So he got two. So at the end of these two breaths, the patient got 800, so essentially 900 milliliters of air. And what you can see, actually, this is a very good, high quality image, is because now the patient got 400 on top of those 440. This patient now has lower compliance, so you're over distending the lung. And so you can see that the end and the inspiratory pressure actually moved up, right? You see it over here because the compliance has decreased. There's more pressure inside inside the lung. And you can see that really the resistance, at least for this second breath, is not increased. Actually, you increase the pressure, but it doesn't look like this one. You see how it increased and then comes down for the same flow. So during inspiration, I would say that this is likely elastic load. And during expiration, if you notice this patient, there's a couple of other things that are seen on this ventilator specifically that is causing this double trigger. But what you see, look at the flow. So during expiration, we always look at the flow to assess resistance and elastance. And I don't see any evidence of PMOS, meaning that the patient is doing effort, but it never, and I'm going to amplify it for those of you that are on the cell phone, you don't see it reach baseline. And this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. And actually, you can see that when the patient got the other breath over here, it was still not reaching baseline. So this patient has massive increased resistance during expiration. Now, you could argue with me and say, well, Eduardo, it's a little bit increased the resistance over here. And I would say, yeah, but nothing like over here. I mean, for this amount of delay to get to the flow to get there, this is very concerning. And you can actually see that the peak flow, it's aborted. There's no peak flow over here. Essentially, it goes down, and there's a massive flow limitation on this circumstance. And so this is a case of this discordant resistance, in which you have normal inspiratory characteristics, so that it's only elastance, and then during the expiration, there's high resistance, and the ventilator is not causing this. You can see that it goes down essentially to baseline. So there's a couple of, so it's not the expiratory filter that is obstructed, because if the expiratory filter was obstructed, I would expect this to have a delay. So it's not the expiratory limb, because the same would happen over here with this. So now that you know that it's, your brain is starting to think, well, could this be dynamic airway collapse? I see that from Siram. And that's the way that you should be thinking. Something is increasing the resistance massively during expiration. There's, and we'll come back to what is causing this in 2 seconds, but we dropped the respiratory rate for this patient. I'm going to show you what was happening to the patient hemodynamically in a couple of seconds, but I want to highlight one of the items that this can trigger is what happened over here. So the patient got an extra breath, and you can see that this second breath seems to have been triggered by the patient. At least the ventilator is highlighting that with this white color, telling us that this was a pressure trigger, and this is set at -2 centimeters of water, and it's still triggered. And you would say, well, can that be PMOS? Can that be the patient actually triggering the event? And the answer, my friends, actually lies on a little known feature on this particular ventilator that has to do with when there is very high resistive load. In this ventilator, it uses a mechanism to compensate, to try to bring the PEEP as fast as it can to baseline. And that sometimes creates some recoil from the circuit, from whatever you want, that generates an auto trigger, so a false trigger. So this is actually, the second breath is a false trigger, and that is causing this. You can imagine on a situation in which the patient has already auto PEEP, it's creating double breath, so breath stacking on the patient without any evidence of PMOS. So this is a false trigger due to an artifact created by the ventilator in situations of high resistance. Inspiration, there's no PMOS, so there's nothing here. The cycle, there's no PMOS. And expiration, there's no evidence of PMOS. So in reality, this is all a type of synchrony created by the ventilator. So now you are in front of this, and you say, why is this happening? And it's time for me to give you a little bit of background on this patient. This patient has a tracheostomy long-term for a failure to wean, and had the trach dislodged because of agitation. And after it got dislodged, the trach was replaced, and minutes later, the patient had a cardiac arrest. Patient was resuscitated, came back, mental status is good. It was a PA, and this is what we get. And so the question is, now you're at the bedside and you see this. So the first thing that we did when we were at the bedside, I'm gonna show you, the patient was on high pressures. We changed the patient to pressure control, pressure support. The patient was awake and able to trigger the breath. Actually, it was overventilated, you can imagine. And we changed him to pressure support because pressure support, if you double trigger the pressure support, you have less less volume delivered at what the patient had. So the first thing that we changed was we gave very high pressure support. You can see over here, because I thought that the patient would require a fair amount. but the patient was doing a good amount of effort to take a breath in and was putting in around 1200 cc's. And you again see the amputation of the of the of the expiratory flow, and you see how long it's taking this patient to exhale. And now compare it. Now this is we're controlling the pressure, so we look at the flow and look at the difference on the waveform from inspiration to expiration. So again, although resistance is increased during inspiration, it's not as increased during expiration. I hope that you're able to recognize that. So the time to decay here compared to the time to decay here, the time constant during inspiration is smaller than the time constant during expiration. And so so this is the blood pressure on the patient as the patient arrived. And I think that this is the teaching message for all of you. Is you can see the heart rate, and then they have these episodes in which heart rate goes up and the pressure goes down. The heart rate continued to goes down. Then something happened and the heart rate goes down. But you can see these oscillations, these massive oscillations on blood pressure. And here you have them again. So every time the patient takes a breath in, and you can see how there's this drop, this pulsus paradoxus, massive drop in systolic blood pressure. And actually, you can see it in the peripheral perfusion of this patient up and down on the pressure on the pulse oximetry. And after we disconnected the patient from the ventilator, this is what happened. So you see from here to here, from here to here. So classic case of massive auto PEEP in this individual. Now the question is why? And so whenever you have a trick that has been replaced and you have this feature, now you know that the inspiratory pressure is not as bad, the expiratory pressure is not as bad, as the expiratory resistance is horrendous. This is classic for a valve ball phenomenon in which you have air goes in, but then as the patient exhales, something obstructs the airway, and the patient has very high pressure. So what I'm showing you here, this is the end of the tracheostomy that was replaced, and all of this granulation tissue, tumor, whatever you want. And so the air would go in, the valve would push back, and then when the patient wanted to exhale, was exhaling through this lever that you have over here. So this is the area that the patient had to exhale. So we changed the tracheostomy for a longer one, and the patient regained the airway. And with that, this is the curve immediately afterwards that we changed. So you see now the flow reaches zero. The patient still taking these deep, large breaths, but as it takes, the patient was on tricolor before all of this. Takes a large breath. You now see the decay, beautiful decay, almost to zero, even though there's PMOS, and you don't see the flow goes essentially to zero during expiration compared to the prior waveform. And so I think that this is the teaching point for all of you is when you have discordant resistances, something is wrong with the airway. Most likely there's an issue with the airway. In this case, it was a classic ball valve obstruction that led to, this patient was on massive amounts of pressures, had a cardiac arrest because of that. He recovered and went out back to recovery, but because it was recognized, but you can see how this could have escalated rapidly. So there's the image for you to remember. Here is the manifestation again. No evidence of high resistance here, very high resistance during expiration. The same happened when we changed to pressure support. Not so much high resistance, very high resistance during expiration. That has to tell you that there's something happening on the airway. So thank you. That's our band rounds for today. Here I put this. I will check for questions on the chat so that we can discuss. There's the CMEs for CCF caregivers and the code so that you can enter it. I would recommend that you do it, scan soon and get it done. And the CRC for our RTs. I also see that Sherry Babic has put in the form for you on the chat for all of you RTs. This is free RTs for all of you. We love you. We want more RTs involved here and learning from all of them. Again, please send us your waveforms in Twitter. Here's our VentRounds page, which is being remodeled as we speak. And you can send Rob or myself, and I know Ariel eventually will get into this fully, and then we will put his thing here so that you can send him. But we are part of the same group, and I'll stop there. Now there's a couple of questions that are coming in. Excellent. How would you differentiate intrathoracic dynamic expiratory resistance from extrathoracic? Well, I voiced a little bit on the differences. If the cause is an expiratory filter, you would expect changes on your pressure waveform, Samid. So usually when it's downstream, before the device, you will see that the pressure is taking longer. And we saw a case actually, I think it's last SEVA VentRounds or two ago, in which you could see clearly that this doesn't return back to baseline, and that's a telltale sign that there may be somebody stepping on the circuit, or the expiratory filter that they put before getting to the expiratory valve is obstructed, or the expiratory valve is adhered or having an issue. The other question that I have is from Ariel. That's a great question. Would the level of PEEP make a difference? Actually, Ariel, that's a great point. The team at night increased the PEEP, and when we showed up, the PEEP was, I think, at 10 or 12. And when we had the scope in, we put PEEP on the patient, and you could see the diameter increase. So it did have an effect on it, but this was just too much. So it was a mechanical issue. At the moment that we advanced the extended length trach distally, it solved the problem. But if you have some sort of, sometimes the obstructions are not removable or bypassable, without a doubt, an increase on the radius or diameter will help you. Great question. Any other questions? I don't see any. So thank you all. Thank you for joining us, and we'll see you in a couple of weeks. Hope you enjoyed this, and we'll put it up on YouTube for all of you to see. There's 3 more videos that are coming up to YouTube soon, so hope that you have a chance to see them. Thank you very much. Have a great day, and that's it.